Hey everyone, and welcome to a brief discussion slash overview of the Big Bang Theory. In essence, we have the story of modern cosmology that rapidly started to unfold. It began rather slow and with ideas building upon themselves. So the universe doesn't revolve around us, or at least the solar system. The heavens are not unchanging and immutable. There's not some entity pushing and keeping planets in their orbits, so on and so forth. And we're not the only galaxy in the entire universe. But things really began to speed up with the equations of general relativity, and of course there were three famous immediate tests that I've listed there. But one of the most important equations in this discussion are the Friedman equations. So in those equations, it looks something like this. There's a number of ways that you can write it. Here's one representation, and basically it describes the expansion of the universe. So what are some of these different parameters? Well, the one on the left is Hubble's parameter. Basically, it is a relationship between how fast this quantity A, or the scale factor of the universe, is changing, divided by the scale factor at any given time. And the scale factor is basically like a kind of a relative number, not an absolute coordinate or distance or anything like that, but it talks about and describes how far apart 2 points in space are at any given time. So at present, the scale factor is defined to be equal to 1, and if the universe was smaller, the scale factor would be smaller than that. And so to get the actual size of the universe, you would multiply that times some distances. So anyways, and this Hubble parameter and this equation is very similar to Hubble's law. But basically, the main point is that if we know how the Hubble parameters changed in the past, as I've written here, we know how the scale factor has changed in the past. So you can measure one or the other. If you can measure the expansion history of the universe, you can know very well what it was doing in different eras. But interestingly enough, what does the scale factor depend on? Well, it turns out it depends on a few different things. The one that we're going to focus on most right now, we'll come back to the geometry of space. The geometry of space is perhaps a negligible term, but we'll come back to that. If indeed the universe is flat, but the main thing that it depends upon is the average mass density of the universe, which can change over time. Um, and so how could you begin to calculate the density of the universe? It's really simple. You just add up how much stuff is in the entire universe. You can do estimations of that because the universe, at least on large scales, is rather homogeneous and isotropic. You can go ahead and add up chunks of the sky and then just interpolate that over the entire sky, or you can learn things from the anisotropies of the cosmic microwave background that we'll get to in more detail later. But basically, if you want to talk about the density of different things, well, the main contributors that we're going to take a look at for now, and we'll look at some others when we talk about dark matter and dark energy, but if you just talk about matter, it's really simple. The density of matter just gets smaller with the is proportional to the inverse scale factor cubed. Why? Because if you have the same amount of stuff and then essentially your universe gets bigger, its density will decrease with inverse volume. Um, Light is a little more complicated, but it's pretty similar. You could, of course, it doesn't really make sense to talk about the mass density of light, but you can, because you can relate the energy that photons have with their actual mass, and that's going to scale like 1 over the scale factor to the 4th power. And that's because, yes, it is getting diluted with inverse volume, but that radiation, those wavelengths are also being stretched by the stretching of space. So, and there can also be the cosmological constant. We'll come back to that. But basically, it's pretty neat. This equation is easy to solve by hand in some of the main epochs of the universe. In the early universe, when it was much smaller, the radiation term would dominate the Friedman equation's overall density. And so you can solve that out pretty exactly and figure out, well, how big would the universe be as a function of time? You can go and figure that out. And then in a matter-dominated universe, that would happen as the universe continues to expand. You can solve that out as well. And then it turns out we're presently in some kind of dark energy dominated universe, or at least that's what it appears to be. So it's pretty simple to go ahead and use these equations just based upon what type of matter you have. Um, so that's pretty cool. Interestingly enough, you can make some more predictions just using this equation. You could say, well, if you go backwards in the past, obviously the density of stuff in the universe was much higher. And what effect would that have on the effective temperature? I'll leave a little link to a paper outlining how you can think about that. But basically, you can figure out that the temperature of the early universe scales like 1 over the scale factor. So basically, if the universe is smaller, since you're dividing by a smaller number, the temperature would get bigger in the past. And then combine that with the idea that we can do particle physics experiments here on Earth, and we know the physics really well up to several trillions of degrees. And so that's really neat. Basically, we know all of the physics that will happen up to a certain point in the early universe when it was really, really, really small. And in particular, you could ask how long after some kind of beginning was this? About a million billionths of a second. So basically, we can at least make predictions of what we should see in the early universe beyond that point. But before that point, we don't really have experimental evidence of such. We'll talk about that later. Of course, one of the most famous things that we measure about our universe is the cosmic microwave background. And at some point, it would have just simply been too hot for any atoms to form. Basically, you wouldn't have protons and electrons coming together. The background radiation would immediately break them apart. But at some point, the universe would have been cool enough such that such radiation would not have been able to ionize hydrogen and would just scatter off atoms and travel through space. And interestingly enough, this is a signal that was accidentally discovered in the 1960s. By Penzias and Wilson. Of course, they got a Nobel Prize, and they ended up scooping a cosmology group in Princeton that was aiming to go ahead and actually detect this cosmic microwave background. A little bit more about what this curve is and why would you even expect to see something like that. Well, basically, pretty much all stars give off some kind of black body spectrum. They're not a perfect black body radiator because they're not truly in thermodynamic equilibrium. But it turns out that our sun is a good approximation of such. And so here's an example on the right of the intensity of our sun at different wavelengths, and you see that it follows the theoretical black body spectrum fairly well. And how does that work? Well, it's pretty interesting. You certainly need your particular object to be opaque and non-reflective. And our sun is kind of like that. Why? Because it's made up of hot, dense ionized gas, which effectively makes it opaque. You can't see through the sun. But if the sun wasn't ionized, then the sun wouldn't be opaque. You'd be able to see through the sun, and it wouldn't make a very black body. But the early universe black body is rather remarkable. It is incredibly close to uniform. And that makes a lot of sense based upon what we know the early universe would have been like. It would have been a near perfect thermal equilibrium, and here's an example of what Penzias and Wilson would have seen had they looked at the night sky. With their technology, they would have looked around and seen that the average temperature, the peak of this black body, is very, very, very uniform with a little band in the middle due to the plane of the Milky Way galaxy. So that's pretty cool. Going back before the cosmic microwave background, if you look at the bottom, you can ask, well, was there a point where even nuclei couldn't have formed? That's an interesting question. In terms of the formation of nuclei with protons and neutrons coming together. And certainly, yes, we know the physics very well of that era, thanks to all of the work done in nuclear physics over the past century. This would have been about a few seconds after the beginning of the universe, after it began, or had some sort of beginning. So we could say, well, what kinds of predictions could we make from that era? Well, if this idea is correct, it should have some kind of bearing on what kinds of atoms we see in our universe. Okay? Dance that you could do. Here's an example of just protons and neutrons coming together, and then two deuterium nuclei coming together and forming helium and a neutron, and so on and so forth. So there's all kinds of simple reactions that you could have occurring. However, some interesting things about this era is that while you needed the universe to be cool enough to go ahead and fuse such nuclei, such collisions would have been relatively rare. There would have been about 1 billion photons for every baryon. And also, the half-life of free neutrons is about 15 minutes. And so, if you had any neutrons beyond this era, they would have just simply and quickly decayed into protons. So basically, your ability to form neutrons, there was this fine dance, or this delicate dance that was going on in the universe. And you can, I'm not going to say too much about this. You can actually make some calculations and pretty simple predictions. It's pretty cool. And here's an example of some of the various reactions that could occur, so on and so forth. And after about 20 minutes, the whole process would have been done. And at this time, what would you see happening? Well, you would have basically free protons or helium-4 nuclei. There would have been smaller amounts of other possible nucleons. You have deuterium and helium-3, and then small amounts of lithium-6 and 7. And one of the problems in terms of making nuclei that are heavier is that there is a lack of stable nuclei in between helium-4 and too much higher than that. And so as a result, if you did actually manage to get them to form, they would quickly decay into other atoms. And so you would be limited. So anyways, it's pretty some nice results here in terms of looking at some spectacular comparisons with measurements in reality. Hydrogen, in terms of looking around the universe, and we can also look at distant galaxies and see, well, what kind of elemental distribution do they have? There was a neat paper that was published recently regarding, I think it was a hydrogen-helium early molecule that we predicted we should see, but we never saw it until just recently. It was really cool. But basically, 75% of the universe by mass is predicted to be made up of hydrogen, and that's what we see. And then helium-4, here's an example, and another one looking at deuterium, where we predict a fairly small amount of deuterium by mass, which is not produced in such amounts in stars. So there's no other source of deuterium except for this nucleosynthesis event. Great. So I want to be careful about my words on this slide, but here's just a simple example of steady state cosmology. There were a number of growing failures of it. It was, of course, being still actively pushed by Fred Hoyle, but we see that by and large, this is not really just something that people liked. That oh, we just really like the Big Bang Theory, or we don't. It doesn't matter. What ultimately matters is which ones fit the data. Here's just a comparison of predictions of the ratios of some different elements to hydrogen, for example. And the Big Bang Theory matches much better with expectations than the steady state theory, as it does for many, many other types of data. And we'll look at some obligatory shout outs, but nucleosynthesis was certainly for that. And that ultimately means that we're all of the stuff that make up us and our atoms essentially were forged in the earliest moments of the universe. So here's a children's book, Older Than the Stars, and yes, the atoms that make up you are older than the stars. Some produced in stars. Here's an example of that. I won't spend too much time on this diagram. We'll come back to some of those. This is also something that you can pause on. This is just the distribution of elements in the universe. So it's pretty neat. And essentially, the Earth has helped concentrate a lot of elements that are not so abundant in the universe as a whole. And you can ask some questions. Well, what about going back farther? I mean, there are some predictions that we have, but at the same time, there's a limit to our ability to probe these energy scales here on Earth. And so what should we do then as a result? Well, that's a good question. Either build bigger detectors, particle detectors, or we need some kind of way to go back farther to test these experimentally. There's a good chance of having primordial gravitational waves, but this basically describes, this is a little graph describing our ability, or the things that we understand really well versus things that we don't understand so well. So that this particular graph was made with white meaning well understood, and darkness is proportional to poor understanding. And so we understand, of course, baryons really well. We understand the radiation very well in these eras of the early universe. But there are some things in the universe that we don't understand really well. We can measure them and very with exquisite precision. We'll come back again to dark matter and dark energy. Why did we end up with these hypotheses? And are there any other better explanations? Well, maybe. We're not sure. But there's a lot we don't know. But there is a lot that we do know. So we do know really well the physics of pretty much everything that has happened in the universe after a second, and even before that time, which means that we can describe about 14 billion years worth of physics of our universe really well. There's some that we can't explain into some interesting questions. So again, it's just a summary of that and a few more. So on and so forth. And I want to pause and just say what the Big Bang Theory isn't. It is really, really a robust description of what happened after about a second coming up to the present in billions of years. What is going to happen in the future and what happened in the earliest moments of the universe, we're not quite sure. Of course, there's cosmic inflation, which would have been before this time of our ability to experiment and detect in various particle accelerators. But at the same time, yeah, we'll talk about evidence for that. What are some strengths or maybe weaknesses of that? What other models exist to describe such phenomena that cosmic inflation actually does explain? But one thing that the Big Bang Theory isn't, that many people think it is it doesn't describe how the universe began. There is no beginning, so it wouldn't make a lot of sense for someone to come in and say, well, hi, you can't explain how the universe began, therefore the Big Bang Theory is no good. That is a really, really large misunderstanding of what the Big Bang Theory actually is and what it claims to be and what it can actually describe. And many things have been predicted and then kind of a neat reflection on terms of the physics that we don't know. Well, it turns out that it makes sense that the Big Bang Theory can't really describe how the universe began because that would be an era that is governed by physics we don't know. Since it's governed by physics we don't know, we can't really describe what happened in that particular era. A kind of a cool example from 1913 was that, well, we were aware of we didn't know about general relativity and quantum mechanics, and it was really crazy that according to known physics, Rutherford's experiment of how electrons orbit a positively charged nucleus should have been impossible. We had no way to explain how the orbits of electrons could be stable. But does that mean a couple of things? Did it mean that all of the physics we could explain were somehow not good? No, it just means that there were new physics that we needed to either discover or come up with. And here's an example of some of the things that we don't know yet. Here's a nice kind of description according to Wikipedia. Some of these might be more established than others. This is, of course, just a loose list, not necessarily from a technical paper, but it's a broad description of some interesting questions. And this is okay. This is really good and exciting. And so there's, of course, an example of some problems solved in recent decades, but this is an important question. Are models or theories falsified by things we don't yet know, or are they falsified by contradictory data? So in other words, do such unknowns like I put up on the last slide, do they falsify the equations of general relativity, or the Friedman equation, or the cosmic microwave background, or Big Bang nucleosynthesis? No. Not in any way, shape, or form. That would be preposterous to claim that, oh, physics of an unknown era falsifies all the physics that we do yet know. But I want to be careful about how this discussion goes forth because I see a lot of people writing about the Big Bang Theory saying, ha, you can't explain how it began, therefore your theory is bad. But that is missing the heart of the model. And here's just a short list of some of the problems solved. I've seen so much writing, in particular from the young Earth creationist community, about the solar neutrino problem. And it was so much, you can't explain this, you can't explain neutrinos, you can't explain the flux. And all of a sudden, egg on the face. And now there are disclaimers saying, yeah, this used to be a good argument based upon our understanding that such astrophysicists couldn't explain the solar neutrino problem, but now we think that it's no longer a good argument. That's ridiculous. But we'll come back to some of these and actually look at what does one do from a young Earth creationist perspective in light of this rather robust model. Anyways, that's all for now. Take care and